A marketing manager clicks a button, and 1,000 miles away, a massive digital billboard inside a shopping mall instantly switches its imagery. This immediate physical reaction to a remote digital command relies on a process known as state synchronization across edge devices. Traditionally, maintaining this connection is fragile. Physical hardware drops offline, network latency delays incoming files, and display screens end up looping out of sync or missing assets entirely. When these failures happen, a consumer sees a black screen instead of an advertisement. That missing second of airtime directly correlates to lost advertising revenue for the operating company. Solving this requires architecting a system capable of bridging a centralized database with distributed physical hardware, instantly and reliably. To understand exactly how this pipeline is built, we are going to examine the engineering portfolio of full-stack developer Akash. Specifically, we will look at a dual-component project listed in his work history, the Prowtech campaign management platform and its companion Android application. Today, we analyze this portfolio as a technical blueprint, focusing on the specific engineering choices that allow distributed hardware to function. By isolating and deconstructing the specific technologies Akash applied to the Prowtech stack, we can map the exact architecture required for real-time edge synchronization. Modern software engineering requires building invisible network infrastructures that connect disparate digital systems directly to the physical environment. Mapping this system starts at the brain of the operation. We start at the CMS Control Center, built with AngularJS and Tailwind CSS for dynamic administrative dashboard rendering. This is the single source of truth, where operators upload images, schedule slots, and target screens. Opposite this sit the physical edge devices. We can determine how these screens are programmed by referencing Akash's second project entry, the Prowtech Android app. The primary framework listed for operating these physical displays is React Native. React Native allows a developer to write cross-platform user interface logic using familiar JavaScript paradigms, applying web development principles directly to a physical television screen. However, alongside React Native, there is an anomaly in the tech stack, Kotlin. Kotlin is required here to bridge the JavaScript interface with native Android hardware APIs. This lower-level access is mandatory to lock a consumer-grade operating system into a restricted kiosk mode for a public mall environment. At this point in the blueprint, the system possesses a capable administrative brain in Angular and functional endpoints via React Native and Kotlin, but they are isolated by a massive communication gap. The system requires a mechanism for the edge displays to know exactly when the CMS has scheduled a new campaign. The standard approach to data fetching is REST API polling. Here, edge displays send continuous requests asking the server for updates. The Android application runs an infinite loop, querying the server every few seconds to check if a new advertisement is ready. At scale, this is catastrophic. If 1,000 mall screens poll the CMS every 5 seconds, it creates immense server load and consumes massive amounts of bandwidth, even when no new campaigns are available. Akash's project specifications reveal an explicit alternative to polling, WebSockets. A WebSocket establishes a persistent, open, bidirectional communication protocol between the client and the server. Instead of looping queries, the display screen performs a single initial handshake, keeping that pathway open indefinitely. The dynamic reverses. The screen no longer asks for updates. The exact millisecond the CMS receives a new advertisement, the server pushes it down the open pipeline. This configuration effectively eliminates network latency while drastically reducing the computational overhead on the server. Ultimately, WebSockets operate as the central nervous system, connecting isolated endpoint applications into a synchronized, real-time distributed network. The Angular interface and the React Native application are strictly surface layers. Hosting a real-time network requires a highly specialized foundational backend. While the Prowtech entries focus on the client side, the broader technical skill section provides the likely candidates for the backend engine. Maintaining thousands of simultaneous connections requires a runtime like Node.js. In Akash's stack, Node.js uses its event-driven nature to handle high concurrency demands. Attached to this foundation are the persistent storage systems, MongoDB and PostgreSQL, handling the heavy lifting of storing campaign media and targeting data. High availability for a continuous WebSocket server introduces a severe deployment challenge, requiring infrastructure capable of instantly scaling compute resources. The portfolio lists Docker for containerizing these environments, combined with AWS and Google Cloud to provide a scalable, globally distributed hosting architecture. Ultimately, a robust edge synchronization system requires precise, scalable cloud architecture to ensure that the front-end user interfaces function seamlessly across the network. Zooming out from the Prowtech diagram, this specific architecture fits into the broader evolution of the engineer who built it. Akash's career timeline begins in April 2022. At that time, his profile was as a front-end developer, restricted primarily to static monolithic web tools, HTML, CSS, JavaScript, and WordPress. By 2024 and through 2026, that baseline expands into full-stack capabilities, incorporating the MERN stack, Python, and cloud-native infrastructure. The Solar by Luminous project provides secondary evidence of this progression, demonstrating his capacity to manage structured enterprise data flow and internal APIs between vendors and employees. This timeline reflects a macro-level shift across the software industry, moving away from building standalone static websites and moving towards engineering complex, microservice-ready ecosystems. Moving beyond the construction of individual interfaces to the management of these interconnected protocols represents a shift towards higher-level system design.